Hi there, this is section 2.8 from James Stewart's Calculus Early Transcendentals book, and we are discussing limits, and we barely introduced the derivative in the last section, 2.7, and that derivative is the limit of the slopes of a secant line as the 2 points on your graph get closer and closer together. And you have that here in this formula. Another way of looking at the derivative or finding the derivative in an easier way is to use the alternative f prime of a equal to the limit as x approaches a of f of x minus f of a over x minus a. Both are equally fine, and I would actually advise using this one here when you just want to find a specific derivative, a specific slope of a tangent line. However, if you do want to consider the derivative as a function, we will take this definition, definition 1, and instead of using a specific value of a, we will take a variable a, where we will allow a to vary, and we'll just replace it with variable x. And so it becomes a function, or the limit of the slopes of the secant lines connecting 2 points on a graph. As those 2 points on the graph get closer and closer together towards a, we will find the derivative at a. But when we replace with x, we're going to come out with a function. And this function is going to have the notation of f prime of x. Good. And we'll call it the derivative of f. All right, so, and it's more powerful to be able to find the derivative, the overall derivative function, because then you can calculate the slope of the tangent at any point on your graph. But if you are just, as I mentioned before, just interested in the slope of the tangent line at a specific point, then you can use the easier formula of f prime of a. So this f prime of a is just going to give you a number, and that number is going to be the slope of the tangent at x equal to a. It's also the instant rate of change at x equal to a. The instant rate of change of the function at x equal to a. Good. All right. So as an example here, determine the derivative of the function using the definition of the derivative, and the definition is the limit definition. This is the definition of the derivative. Good. And I see here that this is function 96x minus 16x squared. I'm going to go ahead and factor out the 16, and that's 16 times 6x minus x squared. I know that then f of x plus h is going to be 16 times 16 times x plus h minus x plus h squared. And if I simplify that, I get 16 times 16 x plus h, take away x squared plus 2xh plus h squared. And if I simplify that even further, I end up with 16 times 16x plus 16h, and this is not a 16, this is a 6, sorry, and that's a 6, and this is going to be minus x squared minus 2xh, and then minus h squared, and that's all multiplied by 16, and that is my f of x plus h. Now I'm going to slowly build that f of x plus h minus f of x, and I have f of x plus h take away f of x. That's going to give me, and if I go ahead and multiply through by that 16, I'm going to get the 96x plus 96h minus 16x squared minus 32xh minus 16h squared, and now I'm going to subtract f of x, and f of x is minus 96x, and I'm still going to subtract minus 16x, and minus minus is plus 16x squared. I can go ahead and simplify that. I'm going to look at various terms, and I see that 96x take away 96x is 0. And I also see that minus 16x squared plus 16x squared is 0. So we just are left with 96h minus 32xh minus 16h squared, and that is my f of x plus h minus f of x. If I go ahead and divide through by h, I'm going to divide through by h. And our plan here, because our next step will be to take the limit as h goes to 0, and you can see that every term in the numerator contains a factor of h, and if I plug in 0, I'm going to end up with 0 in the numerator, and also if I plug in 0 for h, I'm going to end up with 0 in the denominator, so we want to factor that out in calculating our limit. So I'm just going to go ahead and factor it out now, and I'm going to say that that's h times 96 minus 32x minus 16h over h. And now I can cancel my h's, and I'm just left with 96 minus 32x minus 16h. So now I can say that my derivative, f of x, is going to be the limit as h goes to 0 of f of x plus h minus f of x over h. And I have already simplified that difference quotient, and I came up with 96 minus 32x minus 16h. And in that limit operator, h is the variable that is going to 0, and we're only going to plug in that where h appears in our expression, and everything else in our expression is considered a constant, and the limit of a constant is a constant, and the limit of a difference is the difference of the limits and the limit of sums. So I end up with that my limit is going to be 96 minus 32x minus 16 times 0, and that's going to give me 96 minus 32x, and that is my derivative function. Good. I have another example here. Find the derivative f of x equal to the square root of 4 minus x. Again, I'm going to build using the limit definition, the limit as h goes to 0 of f of x plus h minus f of x over h. And so in the first step, I am replacing wherever x appears, I'm replacing it with x plus h. And that is a difficult, if you go ahead and take the limit as h goes to 0 and you plug in h, you will end up with 0 over 0. And usually when we deal with a difference of radicals, we multiply on the top and bottom by a special version of 1, and that being the conjugate, because I can scroll in here and take a look at that square root of 4 minus x plus h minus the square root of 4 minus x, and consider that as an a minus b. Well, if I multiply by an a plus b, then I'm going to end up with a squared minus b squared, because we know that that product does end up being a squared minus b squared. And so that's what I do, and that's what is called the conjugate of that two pair of terms. The a minus b, the a plus b would be the conjugate. If I were given a plus b, the conjugate would be a minus b. So I go ahead and multiply on the top and bottom by that value of the conjugate, and then in the very next step, I end up with the radicals squared minus the radical squared, and we know that square root x times square root x is x, so I can eliminate, if I take the square root of my radicals, I can eliminate the radicals in both of those terms. And then when I scroll in and simplify, I see that my 4's go away and my minus x and plus x simplify, and I'm just left with minus h in the numerator. And so I can factor out the h's in the numerator and denominator, and I'm just left with the limit as h goes to 0 of minus 1 over the square root of 4 minus x plus h plus the square root of 4 minus x. And again, only my h is going to 0, so I'm only plugging in where h is, I'm plugging in 0, and then I can simplify from there. And I see that the denominator simplifies to square root 4 minus x plus the square root 4 minus x, so I have two of them, and my final derivative is minus 1 over 2 times the square root of 4 minus x. Where is the derivative defined? everywhere where the output of the derivative is a real number. That's when we say that the derivative exists at those points. And I see that I have a radical in the denominator. I also have an algebraic expression in the denominator. We do know that we cannot divide by 0. We also cannot have negative values under even roots. So I can see that as long as the expression 4 minus x is positive and never equal to 0, then we're not going to have 0 in the denominator and we're not going to have a complex number. So I say f prime of x will be defined, it will exist, or the function is differentiable at all values where 4 minus x is bigger than 0. So in other words, where 4 is bigger than x. And I could turn that into an interval if I just use that inequality. I know that x has to be smaller than 4, and it can't equal 4, so I know that I've got an open interval from negative infinity up to 4. And that would be where our function f of x equal to the square root of 4 minus x is differentiable. Okay, so here are some other notations for the derivative. We introduced the prime notation, which comes from Sir Isaac Newton. And so you can say for a function y equal to f of x, the derivative can be written as f prime of x. We know that y is equal to f of x, so we can call it y prime. And then we have Leibniz was another creator of calculus, and he uses the notation of dy dx, and that is usually written or said the derivative of y with respect to x. Okay, and we know that it's understood that when you're using this notation, that y is going to be a function of x if you're going to take a derivative with respect to that variable. We can also call it df dx because y was equal to f of x. You might see just this expression, the derivative with respect to x of f of x. You could see a capital D of f of x or d sub x, and that x again is letting you know that's the variable with which you will be taking the derivative. Okay? And please understand that the derivative is the limit of the slopes of the secant lines, and that its limiting factor will be, or its limit will be the slope of the tangent line. So this is a useful term we can call dy dx, which is the limit, which is the derivative, the limit of the change in y over the change in x, or that delta y over delta x, and that's helpful. Also, your f prime of a is going to be the slope of the tangent at x equal to a. And so we would first calculate f prime of x and then evaluate at x equal to a to get f prime of a, and you will often see this type of notation in here. The dy dx with that straight line at x equal to a is understood to be f prime of a. Okay. All right, so what is the definition of differentiability? We will say that a function is differentiable at a if f prime of a exists. And what do you mean by f prime of a exists? This just means once I take the derivative, if I can plug in a value for it and get a real number output. So f prime of a would equal a real number, right? It's not going to be a 0 in the denominator. It's not going to be a negative under the radical or under an even radical. You will have a finite number, and that number can be 0, okay? It just can't be infinity or negative infinity, and it cannot be, you can't have zeros in the denominator. Good. So we say it is differentiable on an open interval, because you'll see that a lot in some of the theorems that we'll go over as we proceed with applications of the derivative. If it is differentiable, if the derivative exists for every point in that open interval. Maybe not at the endpoints, but every point on the inside, you'll have a real number output for your derivative. All right, So in this example, it says determine all values of x where f of x equal to absolute value of x is differentiable, and find a formula for the derivative. So if you recall, your absolute value function as a piecewise defined function is equal to minus x if x is less than 0, and it's equal to x if x is bigger than 0. Okay. And in this case, our problem point is going to be, we won't have an issue for any point less than 0, and we won't have an issue for any point greater than 0. If we were to graph f of x, we would get a v, right? We would get a v on this side, and then on this side. Good. And we know that lines have constant slope, right? They have, from point to point, the slope of the line at any particular point is the same along the line, because slope is an incline. If the slope changed at any point on a line, then it would be steeper at that point, and if you end up with a steeper slope, then you don't really have a straight line after that. So we do happen to know that for x bigger than 0, f of x equal to x has slope equal to positive 1. And for x less than 0, f of x equal to the absolute value of x is equal to minus x has slope equal to minus 1, and that mx plus b. So really, at x equal to 0, f prime of 0, if you use that limit definition for just one specific value, would be the limit as x goes to 0 of f of x minus f of 0 over x minus 0, and that's going to give me x. And so we're going to have that this is going to equal the limit as x goes to 0 of absolute value of x over x, and the limit from the left is going to be minus x over x, which is minus 1. The limit as x goes to 0 from the right is going to be x over x, which is equal to positive 1. And we see here that this is a two-sided limit. The derivative is a two-sided limit, and that limit does not equal from the left or the right, and so it does not exist. So we say f of x equal to the absolute value of x is not differentiable at x equal to 0. There is a sharp turn there. Good? All right, and it says find a formula for the derivative. I would say that the derivative here of f of x, as I mentioned in just taking the graph of the absolute value of x, that it's going to be 1 for, or minus 1 for x less than 0. It's going to be 1 for x bigger than 0. And it does not exist for x equal to 0. So note that x equal to 0 is not in the domain of that derivative function. And if I were to graph it, I would have at minus 1, and I'd have a line up to it. And I would have at 0, it would also equal 1 on the right-hand side, because the derivative would be 1 on every value bigger. All right. We do have a theorem that if a function is differentiable at a, then it's going to be continuous at a. Okay. Above f of x equal to the absolute value of x is a continuous function. It's continuous everywhere. You can plug in any value of x into the absolute value and get a real number output. So it is a continuous function. However, its derivative is not differentiable. So our function is continuous at 0, the absolute value function, but it is not differentiable at 0. So continuity does not always imply differentiability. However, differentiability, if a function's differentiable at a, it is continuous at a. So the converse is not true. Right? So if f is continuous at a, it does not imply it is differentiable. And you can refer to the absolute value function above. That is an example of a continuous function at 0, but it's not differentiable at 0. But if it's differentiable, it is continuous, and the contrapositive is true. The contrapositive is true. Right, so if f of x is not continuous at a, it is not differentiable at a. That is true logically. Okay, and there's a small proof in here. They assume that f prime of a exists because they do assume that f is differentiable at a. That means f prime of a is a real number. And we know that f prime of a does equal the limit as x approaches a of f of x minus f of a over x minus a. And remember, the formal definition of continuity is f is continuous at a if f of a exists, if the limit as x approaches a exists, and really if that limit as x approaches a of f of x actually equals f of a. So we start off with just playing around with an expression for f of a, and we'll just say it's equal to f of a plus f of x minus f of a over x minus a times x minus a, because we can always start off with f of a plus f of x minus f of a, and I'm adding f of a and subtracting f of a, and then in the very next step I go and multiply by a special version of 1, so that's equal. And then I start taking limits as x approaches a, because I want to show that the limit as x approaches a is f of a. And so I use my limit laws. The limit of a sum is the sum of the limits. And then the limit of a product is the product of the limits. And we know that the limit of as x approaches a of f of x minus f of a is actually equal to f prime of a. And we know that when we go to the limit of a constant is a constant, so f of a is a number, so the limit as x approaches a is going to be that number. And when we go to evaluate a limit, we go and plug in wherever x appears, we plug in that value. So if we plug in a here, we get a minus a, and a minus a is going to be 0, and anything times 0 is itself. And so we have shown that the limit as x approaches a of f of x does equal f of a, and we only use the assumption that f was differentiable at a. That's pretty cool. All right. So in a nutshell, how can a function fail to be differentiable? If it's not continuous, so we already mentioned that the contrapositive, if it's not continuous at a, it is not differentiable at a. If it has a corner, if it's got a corner like the absolute value of x, then we can't really, if we go back up to the absolute value of x, if we remember that our derivative is a slope of the tangent line, you can't really draw a tangent line here. Is it that one? Is it that one? Is it that one? Is it that one? We can't define it. It's not differentiable. So if we have sharp turns, we don't have a slope or a direction that the graph is clearly taking at that moment. Okay. We also don't have differentiability if we've got a vertical tangent, because vertical tangents is going to be, I can go up, but I'm not going over. Remember, change in y over change in x. If x is not changing, you have a vertical tangent. And that one you can see from this one. Okay, it says, does g prime of 0 exist? So if I'm just going to calculate g prime of 0, I'm going to say g prime of 0 is going to be the limit as x approaches 0 of the cube root of x minus the cube root of 0 over x minus 0. And that's going to give me the limit as x goes to 0 of x to the 1/3 over x. And I can say that that is going to be the limit as x goes to 0 of x to the 1/3 take away 1, just using the x to the a over x to the b is equal to x to the a minus b. That's an exponent rule. And I see that this is the limit as x goes to 0 of x to the minus 2/3, which is the limit as x goes to 0 of 1 over x to the 2/3. And if I plug in 0, I get 1 over 0, and that does not exist, right? So our function there is not differentiable at x equal to 0. It has a vertical tangent because we have a divide by 0. Good? And that is our derivative at x equal to 0. All right. So finally, in this section, we're going to explore what would the graphs of the derivatives be like, because in section 2.8, we're talking about the derivative as a function itself, and if it's a function itself, then it has a derivative. And so how do we normally do that? We want to, in general, if this is our graph of f of x, we would want to look at where the derivative might be 0. So I see at this point here, and let's say it's kind of at the point 3, this is where f prime of 3 is going to be equal to 0. So I could come down, and if I'm going to graph my function, my f prime of x function, I would go to 3, and I would say the derivative there is equal to 0. Okay? And then I'd start playing around by drawing little mini slopes of tangent lines on either side of that x equal to 3. And so I start noting on the left-hand side over here at, minus 1, even though it's really going to negative infinity, I have a really steep negative. That might be like slope is negative, and let's say it's like minus 10. But as I get closer and closer, I see that I'm going to start getting smaller negatives. If they're all negative, it's still going to be negative, it's still going to be negative, it's still going to be negative. But over here, it's kind of a less negative. That might be like a minus 5, and this might be like slope negative 2. It's becoming less steep, so it's less negative. And when it's less negative, it's actually negative and increasing. Right? It's negative and increasing from like minus 10 to minus 5 to minus 2, ... up to 0. Right? So we know that when it's negative, our f prime of x, what we're graphing, is going to be below the x-axis and increasing. So I might want to do this. Good? And I can do the same argument on this side. I can start off with 0, and then I have positive slopes, right? And then I'm going to have more steep. It's positive, and it's positive, and it's positive. And if they're all positive, and they are increasing as well, we know positive is going to be above the x-axis. And so I know I can continue going, and I probably have something that's above the x-axis. And so this might be my f prime of x function based on that parabola. All right? And on this one, I see it's constant. The slope is constant everywhere on a line from point to point. And I see I can just start from this one. When I go up, I go over halfway. And so it looks like my slope is going to be change in y is 1, change in x is 1/2. So 1 over 1/2 is roughly equal to slope 2. And so I might have a graph here at 2, and I'd have a straight line. And that would be 0 slope 2. Okay. All right, so in general, that's what you might want to do. You might want to say, okay, I've got a 0 here. F prime is equal to 0. Let's say that that's at 1. And let's say that that's minus 1. I also see slope 0 here. And I also see it, let's say call that 2. And I see a slope 2. And so if I were to graph, I would, in general, go to those points. I would go, okay, at minus 1, I'm going to have a 0 derivative. At 1, I'm going to have a 0 derivative. And at 2, I'm going to have a 0 derivative. And so I still want to, on this side of the -1, I have negative slopes. And again, they're increasing. So I might have on this side, they're below the x-axis because they're negative, but they're getting less negative, so they're increasing. I might have, I know I have to come back down, but you can notice that these are positive, but then kind of at this inflection point, that's what we're going to learn, that's what it's called, we start getting, well, they're all negative, they're all positive, but we start to change our orientation and we start getting smaller again and going back towards 0. So we kind of have this hump in there. And same thing goes on this side. We have negative slopes, so we're going to go behind. But we kind of change and we still have negative, but we start to get less negative again. So we would have something that would go down, and we don't know exactly how far it goes down. We will learn later. And again, on this side, we have positive slopes, and they keep getting larger. So we might have this be our f prime of x. Good. This is a point of not differentiable here. At x equal to 0 because we have a sharp turn. So we might have, and on this side we have negative slopes. And they look like they are becoming more steep, decreasing. So we might have, and they're all negative, so we might actually have something that looks like this. And then at 0, we would have that. And on this side, we have positive slopes, and it's not continuous. We might have something that, and it does look like they are increasing, but they're positive, and they're really, we might have something that is, it might not even be a function. Because I know that this one would be negative slopes, and then this one we might have, we're also going down to 0, so it might be something like this. But there's no output there. All right. And lastly, because the derivative is a function itself, it could be differentiable. Again, we can take the derivative of a derivative, and we can take higher order derivatives. Some we're able to take forever more, others we might not be able to, we might zero out after a while. But the notation for second derivatives would be, f double prime, f triple prime, and after a while, like if we did fy equal to f of x, y prime is going to be your first derivative, y double prime will be your second derivative, y triple prime would be your third derivative, and then after that we start putting our numbers in that exponent, we start putting it in parentheses so that we can reserve the f4 to be, f of x to the 4th power. But if you see f with 4 in parentheses, that's understood to be the 4th derivative. Okay. We also have this other Leibniz notation. The derivative with respect to x of dy dx is going to be d2y over dx squared. Okay. And just know that that notation is out there. The third derivative would be d3y over dx cubed, and it would be the derivative with respect to x of the second derivative. Okay, and we'll have many applications with that. We'll talk a lot about motion problems, and they do have nice applications. Okay, such as the position function. If you see if s is equal to the position function s of t, that would give you a distance relative to the origin at time t. So our derivative, which would be the derivative of the position function, is going to be ds dt, and that is the limit of the change in s over the change in time as the change in time goes to 0. and that's going to give us a displacement. That's going to be a distance over time, and so you can see that that's going to give us a velocity. Okay, and with velocity, if we take the derivative of velocity, we're going to get, this is going to be the distance per time is going to give us like a meters per second squared, and that's going to give us an acceleration. Good. And so we do have many opportunities or useful things to do for higher order derivatives. And of course, the fourth derivative of our position function is going to be the rate of change of acceleration with respect to time. How fast is the acceleration changing? And if you think of that, it does have a special name, and that is called a jerk. And that kind of makes sense. If you have a sudden change in acceleration in your car, you might experience a little bit of a jerk. So it seems to be appropriately named. All right, I'm going to stop here. In our next video, I'm going to go over a quick way to calculate derivatives so that we can move forward with really useful applications. Take care.